now, well, it's a challenge of bringing us from lunch back into the world of, well, hybrid search, and he'll be sharing how to combine inverted and ANN indexes for scale. So please welcome Anubhav on stage with us.
Thank you. I hope you all had like a good lunch and enough caffeine in your bodies to get started with this session. So I appreciate that you all have deep intimacy with searches and how to like run them in relevance ranking. I come from the world of databases, and part of my motivation here is to bridge the gap between these two worlds. And if I'm successful, hopefully by the end, you'll all leave with a little bit of appreciation that search and ML and databases have a lot more in common than we would otherwise think. Before we get started, a little bit about me. So I'm a software engineer. I've been working at Rockset for a couple of years now. Rockset is a real-time analytics and search platform. It's built on RocksDB. Before this, I was at Facebook for 5 years, where I was working in a rule engine team. In those 5 years, there was a clear transition from heuristic rules to ML-based rules. And it was visible to everyone, very noticeable. And I anticipate with this advent of language models, it's only going to intensify. In this talk, we'll be talking about what we at Rockset called a converged index. And then how did we add an ANN index to this converged index to allow SQL queries with vector search. Then we'll also talk about some databasey concepts like sharding and how did we allow easier updates of vector embeddings. And lastly, we'll also talk about how to avoid contention between indexing and queries, which is a hard database problem, and what we did at Rockset to solve that. Cool. So we have inverted indexes. All of you, I'm assuming, are familiar with this. But essentially, it looks like a map from a term to a list of documents which contain that term. And then you can rank this list in however way you want. In this example, you have 2 documents, and each term has a posting list of doc IDs associated with that term. However, this inverted index is usually not sufficient by itself. So what we built in the form of a converged index is, given a document, we index it 3 ways. So the first store is a row store, which is essentially a mapping from a doc ID to the contents of that document. So in this case, imagine you have documents just containing a field name. So the row store will be r.0, the doc ID, followed by the name is this, r.1.name is this. Then the second store is called a column store, where essentially the doc IDs and the field IDs are reversed. So you have the name of the doc ID 0, name of doc ID 1. And the advantage this flipping gives you is that it's much more efficient to do large scans, because now keys with the same prefix are in a contiguous section in your storage. So you don't have to like hop around in the on disk. And the final is the search index, or the inverted index, which we talked about. It allows you to do things like get me all documents where name is, say, Dhruba. Now the name.dhruba mapping is part of the key. So you can quickly query your key space to find all documents which contain this particular attribute of a particular field. Under the hood, we use RocksDB. It's a key value store which came out of Facebook. It has what is called an LSM architecture. It's great for ingest throughput. How it works, let's get to the next slide so we can quickly walk through. I won't spend too much time on it, but essentially you have a bunch of writes coming in. These writes are buffered in memory in what's called a mem table. Things here are sorted, and ever so often, these writes are flushed onto disk in what's called an SSD file. There's a background process which is called compaction, which ensures that keys in SSD files are also sorted. So if any of you are familiar with garbage collection, an analog you can draw here is similar to how objects move from newer generation to older generation as part of garbage collection. It's sort of similar to that. But the key part here is that when you're doing updates, you don't need to find the position of a document in your database. An update to an existing key or an insertion of a new key simply is a log append. And then there's a background process which sorts it to make faster lookups possible. And finally, we get to the heart of why we are here today, which is ANNs. So the key observation to make here is that vector search or vectors are not, well, they are different and they enable a whole array of applications, but they're not all that different. In essence, a vector is just an array of floats. Vector search is just a new query processing algorithm. So they have a lot more in common with databases, and a lot of the techniques and studies and research which have went over decades to allow fast database queries can sometimes be directly applied to also allow fast vector search queries. So inverted file index, which we'll get to, is one of the techniques to allow approximate nearest neighbor search. That's similar to an inverted index, which we talked about. Similarly, metadata filtering, that's just a SQL where clause. Or k nearest neighbors, that's just an order by distance limit k, where distance encapsulates, could be like the Euclidean distance um, or something else, which inner dot product, cosine similarity, whatever it is that you want to measure distances between your vectors based on. All right, so far so good. All right, cool. So before adding ANN indexes, I guess it's prudent to ask why add them in the first place. And the heart of the answer is that it allows better search experience, better user experience, because vector search in essence captures semantics from your data, which are hard to otherwise write down in queries. And now once you have an encoder which is able to capture these semantics, emits out a vector, and now you can run queries in this high dimensional vector space to find things which are similar to this particular query. Example queries could look like, find me all restaurants which this user might like. This is a vector search query. And you could filter it by radius. You could filter it by restaurants which are open right now. Similarly, you can find all images of cat, which might be a vector search, uploaded last week. And so on. The list goes on. But the key observation to make here is that vector search by itself is rarely enough to drive value to users. You usually need to augment it with some sort of metadata filtering to show the most relevant results to your users. And that's what Rockset's converged index was augmented to do. You can imagine your documents stored in whatever database you have. Could be Kafka, S3, Postgres, DynamoDB. And then you could augment this data with vector embeddings from any of the popular models from Hugging Face, OpenAI. And all of these documents with the vector embeddings are stored in Rockset in this converged index, such that it allows fast search and analytic queries. Some known design challenges which come in trying to solve this are that index building is usually expensive. Even after you have the vectors, in order to filter down vectors which are close to a particular query vector, that's a hard algorithm problem. The difficulty in that problem, which I think we'll get to in a future slide, actually just the next slide, is because of the high dimensional space that you have to query in. And then some other challenges here include, how do you search across metadata and vector embeddings? And then the rest are essentially database challenges, sharding, updates. The last one, something I'm really excited to share with you, which is how do we avoid contention between heavy indexing and queries or search? We came up with, well, we'll get to it when we do towards the end of this presentation. So ANN indexes or approximate nearest neighbor, essentially it is, you have a query vector, which is an array of floats. It could be anywhere from 100 floats in an array to 1,500 floats. And you have to find k closest vectors to this query vector. The challenge in solving this fast comes from the high dimensional space, which really makes existing techniques such as KD trees not possible, because they're not able to like prune the search space as effectively in higher dimensional. And that's why there are a bunch of fancy algorithms, which have already been talked about in today's talks and yesterday's, which try to solve this approximate problem. All of them have their own parameters, which you could tune, like you could go for faster index builds at the expense of recall and so on, so on. You can learn much more about this at ANN benchmarks, which has also been mentioned multiple times in all these sessions we've had over the last 2 days. The two more common ones which I want to focus on today are inverted file index and HNSW. Both have their own trade-offs. HNSW probably has the best search performance, but it comes at the expense of larger indexes and slower insertions. And inverted file index has decent performance and low memory usage, and it's easy to plug into existing inverted index, which we talked about, which is why we have adopted this as our algorithm for k nearest neighbors. Yeah, this slide just shows build times for different algorithms. All right, so how does inverted file index works? If any of you remember your k-means clustering or centroid algorithms from university or something, it's essentially that. Like, so let's ignore the high dimensional. Let's imagine just a 2D space and vectors represented as points in this 2D space. In order to find vectors which are close to a query vector, what we first do is we build an index. And that index essentially identifies, say, 1,000 points, which are marked as centroids. So you have a 1 million, 100 million vectors which are in your database. You just identify 1,000 centroids. And now when a query comes in, all you have to do is you have to figure out, okay, which is the centroid which is closest to this query vector. Quite needless to say, it's possible that that query vector is at the edge of two cells and stuff. So you don't just limit your search to the cell that the query vector is placed in, but you can configure it, but you essentially query a number of cells close to that query vector. And now you've already pruned your search space, and now you can, within this search space, find vectors which are closest to the query vector. How did we add this index to our converged index? So we use Phase, which is Facebook's library, which has multiple index implementations, I think including HNSW. So we use Phase, given a bunch of documents with their vector embeddings. We use Phase to compute which document is associated with which centroid. Along with this, Phase also returns what is called a residual, which is just a measure of the distance of this point from its centroid. It's not relevant for the rest of the talk, but I'll mention it nonetheless for completeness. Once you have these centroids, it's, again, worth noting that the amount of data needed to store the centroids is not that much. All you need is just the centroid ID along with the vector associated with that centroid. It's a small amount of data, can be kept in memory, and that's indeed what we do. So yeah, that's how eventually the table looks like. You have documents. Each document has a vector embedding column. This embedding could be generated through any model. And each document now is associated with a centroid and a residual. Once this extra attributes are associated with the documents, the rest of the indexing process is just the same as before. So you again build all three stores, a row store for doc ID lookup, column store for large scans, and inverted index for point lookups. So you have the index. Now, what do you do with it? So one key challenge which we were faced here was, what's the language in which people will express their vector search queries on the application? And we have been using SQL for a long time now. So what we decided was to just use SQL to enable these queries. So imagine you have to run a query where you have to find all restaurants which a particular user might like in a particular location. A query like that might look like select name from restaurants where location equals blah. And the highlighted portion is the vector search part of the query, where essentially you just sort the results, you order them based on your distance metric, and you limit the result to just 5 results. There were a few conversations in previous sessions about relevance of vector search, and it might returning vectors which are not relevant, but it still returns k vectors nonetheless. So it's possible to filter your search results by a similarity threshold. So you could have something like the distance less than a particular threshold or greater than a particular threshold extra filters in your queries, which will result in the query not necessarily returning k items, but ensuring they meet a certain relevance criterion. So under the hood, given this query, under the hood, Rockset understands that this order by clause is in essence a vector search. It again queries phase to figure out, okay, this order by distance embedding is your column in the in the existing database, and the query is the query vector. So what Rockset does is it now sends this query vector to phase, and phase returns it the centroid corresponding to this query vector. It does not return just one centroid, but imagine it returns 3 closest centroids to this query vector. And then we rewrite this query by replacing the order by statement as just a filter on whether the centroid is 2 or centroid is 4 or centroid is 1000. And that's it. Like the vector search part of the puzzle has been solved by this point. What you're left with is a basic SQL query. And there are decades of research which have gone into how to efficiently run SQL queries. And that's what's left to solve from here onwards. So given this query, the challenge is to run it as fast as possible and as cheaply as possible. This, in essence, is essentially like a selectivity estimation problem. Like all you have to figure out is, given this query, how many documents in your database match the first filter where location equals blah? How many documents match the second filter, centroid equals 2, third, fourth filters? And how many documents match composites of these filters? So how many documents match centroid equals 2 or centroid equals 4 and so on? And how we solve this challenge is by adopting a cost-based query optimizer. I won't get into too many details, but essentially it builds histograms on different attributes and identifies what are the possible selectivities of these filters. It does some basic decorrelation, nothing very fancy yet. But once it has done that analysis, it now knows from the converged index which is the best store to query for particular sub parts of your original query. All right, cool. So far, so good. All right, so now we get to what's already been discussed a bunch of times in these sessions, which is metadata filtering. So if any of you are familiar with this space, you would have heard of like post-filtering and pre-filtering. And essentially at its heart, like pre-filtering is great when you are running highly selective queries. So what you can do is first run the filters, which will already prune your search space down to a few documents. And now you can simply run like a linear scan and find the k closest documents from your query vector. And then you have post filter on the other end of the spectrum, which is great for not so selective queries. So you first do the filtering by vector search, and then you apply the other predicates in the query. In our case, we have what we call a single stage filtering. Essentially, if you remember the earlier example, given a vector search query, we first query the library to identify which centroids this query belongs in. That part is done regardless of the other filters in the query. And once you're down to a query like this, from here on, the cost-based optimizer takes over, and it figures out which part of the query will access which index in the database. So essentially, filters are running interspersed with vector search filters. So it's hard to say which is running first. It depends on, for example, if you're finding restaurants, say in here in Berlin, there would be a variety of restaurants in your radius. So it's possible that in this case, you apply the other filters, say restaurants which are open right now, first before finding vectors which are closer to the query. All right. And then again, I'll not spend a lot of time on this, but at Rockset, documents are sharded based on the document ID, which means given a query, it needs to query all shards of the database. Internally, every shard has an associated set of microshards, which is for easier resharding. And each shard has its own index. This is the key point to note, because what that allows us to do is, given a query, we just run it on all shards independently, and then just merge and return the top k results back to user. And finally, the last part of the indexing puzzle, which is how do you handle updates? This could include, can I add new vectors to my database? Can I update existing vectors? Say the model parameters which you're using to encode your semantics into a vector, those model parameters change. You might want to update a subset of your documents in the database. So does your database allow that? Naively inserting has speed and accuracy problems. You can draw an analogy with a binary search tree. In this case, what might happen is, imagine you have a lot of points which keep on going to the same centroid. So now this centroid might keep on becoming dense, while the other centroids, like the other cells, still have only a few points within them. So what's needed is to periodically retrain your index. You need not do it on every update, but ever so often, it's important to sort of recompute that index so as to keep your recall high. All other updates which are going in between these index builds, those are immediately variable. So if you have a new vector which goes in with associated, sorry, if you have a new document which goes in associated vector, that will still be indexed, and any subsequent query which runs, which includes that cell, will show up this document as a potential result. And what makes solving this problem slightly easier for us is that at Rockset, like, every field is mutable. So imagine you have a document where the vector embedding is updated. We again query phase, and it again returns us a new centroid and a new residual. So for this document, which can potentially contain a large number of attributes, only 3 attributes are changed: the vector embedding, the centroid, and the residual. And in RocksDB, which is our key value store, only the keys associated with these 3 attributes need to be changed. This avoids a lot of heavy work associated with just naive updates. This also means that any updates are queryable within hundreds of milliseconds. In fact, as part of an earlier slide I meant to share, where we have demonstrated 20 Mbps at 70 milliseconds of data latency. Yeah, we're confident like that's doable. And this is the final part of my presentation here, which is how do you avoid CPU contention between indexing and search? So here, essentially, the problem is that it's hard to predict the future. Like, you don't know, you deploy an application, it's getting its stream of updates, and users are running queries on this application. It's hard to predict which of these would spike. And oftentimes, applications are highly sensitive to ingest spikes. Applications for vector search are also sensitive to index builds or index retraining, because these take away CPU on your compute, and you're left with less CPU for the searches. And that just results in a bad user experience. So ideally, these 2 parts of the problem, the ingestion and the indexing, and the query compute, should isolate. So one simple solution here would be that you have all your updates going into one cluster, and then ever so often it reindexes, it retrains, and it then sends that index out to your other host of machines which are handling your queries. That would work. That is similar to how daily ETL pipelines, one could argue, work. But the challenge is that is not real time. So when you have updates being added, sorry, if you have new vectors, new documents being added, or you have existing documents being updated, even when the index does not need to be retrained, even those documents are not accessible to queries. Now, if a new restaurant is open up and you are just interested in restaurants which this user might like, maybe that's not as relevant. But imagine a restaurant runs out of some key ingredient and it's not able to serve some items. Now, you definitely don't want to show that restaurant in your search results, and you want to stop showing that restaurant as soon as possible. The same goes for, say, building a recommendation engine which shows viral reels to users. Now, here you would probably be interested in not just which reels are viewed the most or which reels this particular user might like, but you might also want to augment your search results by recency. So reels which are going viral right now, or something of that nature. It's easy to come up with many examples where the ability to have new documents which are added show up in your query results as soon as possible just allows to drive a lot of user value. So how we do this is what we call compute separation. Again, obviously you can't avoid having a different set of compute nodes for your ingestion and a different set of compute nodes for your query. That's unavoidable. But how do we address that real-time thing? Is we have a shared hot storage. So you have a rack of machines with their SSDs. Here, the left side is where the data stream is coming in, and the right side is where queries are happening. You are obviously free to also run your queries on the ingest cluster. The ingest cluster patches things in memory ever so often, flushes it, and it flushes updates to disk. It does not flush them to a local disk. It flushes them to shared storage. This flushing can be delayed. And in order to narrow down that delay as low as possible, what we also do is that updates which are made in memory are streamed live to all other query instances. And that essentially allows us to query on a different compute cluster while keeping the data latency quite low. And it's possible to have multiple compute clusters in this setup. So you can have one ingest cluster, which handles your data stream coming in, which handles your index retraining, and a bunch of different compute clusters, each targeted towards a particular application. So you can have a compute cluster, which, for example, handles your search experience on your main user-facing app. And then when people inside your org, say, want to run some ad hoc analytics, you can spin up a new compute cluster, which can be used to address queries coming in for those ad hoc queries. And you can also scale these compute clusters or ingest clusters independently. So you can have a massive number of nodes in your user-facing compute cluster while keeping the costs of your ad hoc queries down to as low as possible. All right, thanks for bearing with me after lunch. That brings us to the end of my presentation here. If there's anything I want to take you, sorry, I don't want to take any of you with me. If there's anything I want you guys to take away from this presentation, is that all vector search applications will employ some metadata filtering. So you need a system that can do both of these, that can do efficient vector searches and can do metadata filtering and do both of these cheap and fast. Databases and machine learning have more in common than we think. And essentially, both these fields can benefit from a diffusion of ideas across each other. And then whatever you do, design for scale. We live in a world of Googles and Facebooks where you never know which app blows up, and it's important that you don't kick sharding, isolation, and other important properties in your system down the road. All right, thank you.
Thank you. Do we have questions? Yes.
Thank you very much. Can you please re-explain this idea of that centroid?
Yeah, sure. So imagine you have points in a two-dimensional space for simplicity. And what the library already does is it decides on a small number of points, which are called centroids. And every other point in your database is associated with one of these centroids. So essentially, your space is partitioned into cells, and each cell contains a number of vectors. And now when a query comes in, you just concentrate on cells which are close to this query vector. So you have a new point which comes in where you want to find other points close to this point. You limit your search to this region marked in purple.
Hi. You say that the index is in memory and the vectors, the embedded vectors, probably on the SSD. So how you control the latency? The maximum bandwidth from reading from SSD in normal instance in the cloud is, I don't know, 200 megabytes per second. So it will slow down your query significantly.
So your question is that the index is in memory, but the documents are in disk. So how to balance latency?
Leave the metadata, only the embedding data is on the disk.
Yes, that's correct.
Yeah.
So yes. So in this example, only the information about the list of centroids you have and the query vectors, that's small enough to be kept in memory. Rest all is fetched from disk. We have a shared tier of storage. So it's not just one node with disk associated with one compute cluster. We have a bunch of these. So bandwidth in a sense is sort of like you get the bandwidth from all of these nodes. Not all of your data needs to be fetched from disk on one node. So that helps in that problem. The latency, like we found S3 is definitely very slow. Like S3 easily has like 200 to 300 millisecond latency.
We are not talking on S3 here.
Yeah. So for this storage, we have seen like less than I don't know the numbers at the top of my head, but if I were to guess, I imagine we've seen tens of milliseconds of latency in querying from remote storage. So it's not that lot. And when for a particular index, when the data for that index is spread across not one, but many disks, I think bandwidth problem is also not that.
Okay.
I mean, it is still a problem, but you can solve it using a shared
Okay, thank you.
Thank you, great talk. Expanding on this, how would the recall, I would imagine recall would suffer more and more data points, because a particular Voronoi cell would get more and more concentrated with data points, and then they become indistinguishable because they all get squished into a centroid. So how do you make sure that recall doesn't suffer as you add more and more data points to this type of framework?
Thanks for that question. That's a great question. So essentially, that's why we need to periodically retrain the index after every so updates, not necessarily after every update, but after a batch of them, you do need to retrain the index to come up with new centroids. Because as you said, like if one cell keeps on getting a lot of data points, you might need to break it into two cells, each with their own centroids. So you do need to retrain the index after every few updates.
One follow-up. Can you increase the number of centroids, or do you always keep it the same and just reallocate them into like a crowded space?
I believe that's configurable. Like Phase already allows you to decide how many centroids you want for your documents.
More questions? Yes.
Thank you. The SQL query actually needs to kind of scan all the available results and possible results out there now. So this is, I mean, do you have plans for ANN, like something which is faster than simple scanning of possible results?
So that's not entirely accurate, because when a query vector comes in, you already prune the search space down to a few cells which are closest to that. So approximation has already taken place at this point. Like not querying all vectors in your space, you are querying say just 3 out of 1,000 cells. Secondly, within even these cells, we don't do a brute linear scan. So when the query breaks down into something like this, we may leverage the inverted index to say first filter by location, and that gives us a list of doc IDs. And now the other filters are only applied on top of doc IDs, which have already matched equals Los Angeles filter. And eventually, whatever results you get out of this do need to be still sorted on the distance metric. That's an extra thing that you have to do at the end, but you have to do it anyways in ANN. Thanks.
More questions? Yes.
Thanks for your talk. I have a question on what does the query look like? So I think in the previous step and the previous slide, so here you say approximate the similarity index based on the embedding and the query. But for this example, what does a query look like? So what is the query?
So the query would be a vector of floats. So in this example, essentially, whatever signals your application would have collected for a particular user, which you deem are useful to infer which restaurants this user may like. So whatever signals you calculate, those are fed into a model, and that model returns you a query vector, and that goes in here.
Any more questions? Oh, yes.
Thanks. Yeah, thanks for the talk. I had a question regarding, like you mentioned that afterwards there's like you need to kind of filter by some distance or sort by the distance. So that like, is it also happening on this layer, or is it like some sort of another phase after returning these restaurants?
Yeah, good question. So that doesn't happen by default. You need to add an extra step if you want to have a cutoff threshold for distance beyond which you'd want to stop showing results. That needs to be an extra clause.
And maybe another question I had in mind was, do you also have users which have requirements for joins on the vector property, and what kind of join semantic is there users usually use or require?
Yeah, no, that's a good question. We have had users with join requirements, and we do support full SQL joins. So you can run your sort of like your vector search on one table and then join it with a filter which is applied on a separate table. So we support full SQL joins. You mean a join on the vector properties? How? I'm not sure I understand the question.
Vector similarity is basically if you have two vector sets, you want to join and say the vector property.
I see. So something like you have vector embeddings associated with the documents in table 1 and vector embeddings associated with the documents in table 2, and you somehow want to join across these two spaces.
On a similarity threshold or on a canon.
I don't think we support that. Yeah, I imagine like vectors. Yeah, these vectors are coming from a different space. So yeah, I don't think we support those kind of joins. But I'm happy to like follow up with that. Maybe I'm misunderstanding the question. We can maybe have a chat later.
So last call. One last question. Okay.
Why did you choose to follow to implement the SQL and not follow the Elastic stuff, the SL part, which is more common for search?
I don't have a good question to that because
good answer.
Yes, I don't have a good answer to that question. I think arguments can be made on either side, like because we definitely have had customers who have moved away from Elastic because they did want to use native SQL and they wanted joins. So I imagine it's a debate which you could have both sides on.
So let's thank Anubhav. Thank you very much.